Do a little teaching. So right now you need to take out a notebook, pause this video if you need to do that, get a blank piece of paper ready, and at the top you can write down today's date. For you it's probably 9/23, but some of my students are going to get this on the 24th. And we're going to talk about mass, volume, and measurement. These are super important concepts in chemistry that are going to come up over and over again all year. So let's go ahead and get started with mass. And whatever I'm writing here, you're copying this down. These are your notes. My quizzes and tests are open notes, so you can use whatever you copy down here during a quiz or a test. You won't be able to see my copy during that quiz, so you got to have it in your own notebook. So DEF stands for definition. And we're going to start with mass. Mass is the amount of stuff in something. So you can tell right away that my style with these definitions is very, unscientific, really. I like to make things as easy as possible to understand. This is not the textbook definition of mass. In fact, if you look it up, you're going to find there's lots of different definitions of mass out there. I think my definition is the easiest to understand, right? If you've got a thing, like a person, like me, I'm made of stuff. I've got bones and skin and, however much stuff I'm made of, that's my mass, okay? And things that have more stuff in them, they have more mass. Now, stuff, what stuff really is, if you want the scientific word, stuff means matter, okay? So matter is what pretty much everything in the universe is made out of. Okay, matter, like rocks are made out of matter. People, animals, even things you can see through are made out of matter, like water, and even air is made out of matter. Okay, all of these things are made out of matter, so they have mass. They're made out of stuff. Even the air is made out of stuff, matter. You can feel the atoms when you wave your hand in the air. Even though you can't see it, it's there and it has mass. Okay, so mass is that measurement. Now, when we go into the lab, what we're concerned about is measuring the mass. So measuring mass. We use a scale to measure mass. That's probably the most common way to do it. You just have this electronic thing, and you put something on top of it, and the little readout on the front of it gives you a number, and that tells you the mass, and that's pretty simple. You can also use a balance, like if you've seen one of these things that tips back and forth, that's another way to measure mass. But scales are definitely the easiest. And when we finally get into the lab, if I can finally make it into school without sickness in my household, then you'll be able to use the chemical scales, and those are able to measure very, very accurately. You can even breathe on them, and they're so accurate that if you blow on it, like, it'll read that number from your breath. Because again, air is matter, and if you push some air onto that scale, it's going to measure the mass of that air that you just pushed on there, okay? So we use a scale, and then it measures with very specific units. Now, units are grams. That's a little g. Hopefully this is review from 9th grade for you. So when you get the mass of something on the scale, it tells you how many grams, okay? So units are kind of like, grams are kind of like pounds, but it's not exactly the same as that, right? So units are grams. We also, for very heavy things, we can use kilograms. And that prefix kilo, that means 1,000. The abbreviation for this is kg. So this means 1,000. So if you have a kilogram, what you're really talking about is 1,000 grams. Okay? Pretty simple. For really tiny things, we could use milligrams. And that's an mg. This is going in the other direction. Instead of 1,000, we're going to have a thousandth of 1 gram. Okay, so this is for really tiny things. Just to give you an idea with some examples, okay, EX means example. A paper clip, that's about 1 gram. Okay, another example, a bottle of water. And I mean like a big bottle of water, a nice, like an Nalgene bottle of water. Typically that's going to be about 1,000 grams. Okay, or we know that 1,000 grams is the same as a kilogram. You could also say that that water bottle is 1 kilogram. Same thing, okay? So that's the basic idea of mass. Now, one important thing you need to know, okay, is that mass is not the same as weight, okay? Weight tells us how heavy something is, and weight depends on gravity. Here on Earth, I have a weight, I don't know what it is, I haven't weighed myself in a while, it's probably like 160 pounds. So on Earth, let's say I weigh 160 pounds. Up in space, you know how things float up in space? There's no gravity. Up in space, I weigh 0 pounds, right? But mass is different. When I'm down on Earth, there's a certain amount of stuff in me. It's like about 50 kilograms of stuff. And when I go up in space, there's still the same amount of stuff in me, right? Like all the bones, all the blood, all the tissue, when I'm up in space, that's all still part of me. So up in space, I still have a mass of about 50 kilograms. So mass does not depend on gravity. Even where there's no gravity, I still have the same amount of stuff in me. But weight is not the same. Weight is how heavy you are, that depends on the gravity. Okay, so be aware of that. It's so important that I think it's worth putting in our notes. Okay, mass is not weight. In fact, you might see that on a quiz. Hint, hint. New topic. Volume. Definition. Volume. And again, I'm going to keep this really simple. Volume is how big something is. The textbook definition says volume is how much space an object takes up. That's the same as how big, okay? Measuring. And once again, I should note volume and mass, not the same. Typically, bigger things have more mass. They have more stuff in them, but not always. I mean, think about clouds. Clouds are huge, big volume, but they're so light, they float. Not very big mass, but big volume. Okay, so not always the same. Measuring. We use in the lab a graduated cylinder. Okay, and this week, your at-home assignment, let's see if I can dig that up right now. Where am I? Science of chemistry. Your at-home assignment this week is to learn how to use a graduated cylinder. And I kind of try to teach you in here. This thing over here, this is a graduated cylinder. Okay, so you're going to learn how to read that and practice for your at-home assignment. That's what that looks like. If you look at the top of the graduated cylinder, you can see, oh, where is it? I've got one where it shows the top somewhere in here. There it is. You see the letters ml. That is the unit that we use when we're reading these graduated cylinders. So units are liters. That's a big L. But also, just like mass up above, remember mass, we didn't just have grams, we also had kilograms and milligrams. With liters, you can do the same thing. We don't often go bigger. Like, I've never heard of anybody measuring anything with a kiloliter, but I've heard milliliter a lot. This is pretty common. And that, just like the grams, milli meant 1/1000th, and it still means 1/1000th right here. So a milliliter is much smaller. Examples to give you an idea of what these things mean. A big water bottle, like if you buy one that's refillable at the store, is 1 liter. Okay. Trying to think what else. I don't know. That's pretty it. A milliliter is about this much. If you just pinch your fingers pretty close, that space in there, that amount of space is about 1 milliliter. Okay, and you can fit 1,000 of those into a big water bottle. So that's how we measure volume. And that's pretty much all there is to it with that. I'm just going to double check from my prior lecture to see that I didn't miss anything here. We got mass, Nalgene, yeah. And now, how to say it. Yeah, I forgot about that. I don't often like to say milliliter because it's kind of clumsy. A lot of L's. So a lot of chemists, me included, we don't say milliliter, we just say mill. Okay, so another example of how to say it. If you have the number 4 ml, then we say 4 mils. And it's a lot easier to say mils. So you'll hear me say it that way all the time. That's how I prefer to say it. Last topic. Accuracy versus precision. When you do a measurement in the lab, you want your measurement to be accurate and you want it to be precise. You want both. Okay, they're not the same thing. I need you to know the difference between these two. Accuracy asks, how close is my measurement to the truth? Right? Like when I put something on a scale, this pen, and if the scale says 5 grams, how do I know this really is 5 grams, right? I'm trusting that this scale is accurate. The only way to test if it's accurate is to use a known mass. So in the lab, we can, here I'm going to draw a scale here. Here's my scale. There's the platter where we put the mass, and then here's the readout. So maybe I go in the lab and I put this thing on there, and I actually have these in the lab. This is supposed to be a metal cylinder, and on the metal cylinder it says 50G. That's because this thing is a special 50-gram mass that I bought, and we know that it's 50 grams. So when I put it on the scale, what if the scale doesn't say 50 grams? What if the scale says 48.29? Right? Is that accurate? Well, no. With 2 decimal places here, I would expect this scale to be pretty spot on. I want to see 50.00. 50.01, maybe. That would be fine too. But 48, forget it. Okay? Not accurate. That's bad. We want our measurements to be accurate. And the way we know is, again, we test it with a known mass. So this right here is a known mass. We know how much the mass of that thing is, so it can tell us whether the scale is correct or not. Okay, so that's accuracy. Precision. How close are multiple measurements to each other? Right? You know, you expect when you put something on a scale, let's say it says 48.29, if you pick it up and put it back on the scale again, you know, you would expect that it's going to give you the same number again. But not always, right? Not every instrument is precise. If it keeps giving you the same number over and over again, that's a good thing. That's precision. You want that, right? You don't want it to like have randomness built into it, right? So, for example, a scale gives 3 measurements. Right? I take the same object and put it on there 3 times. What if I take this known mass of 50 and I put it back on the scale 3 times? The first time I put it on there, it gives me 49.00 grams. Second time I put it on there, I expect to get 49 again, but nope, it says 51.00 grams. So now I'm confused. I pick it up and I put it back on there a third time, and this time it says 50 grams. Well, what does all this mean? Well, it means 2 things. If I take the average of these 3 numbers, the average equals 50.00 grams. I picked these numbers so that the average would turn out that way for this lecture, right? Now I got to do a little shuffling here to get down on the page. So if my average is 50 grams, well, that's good because I know that the real mass is 50 grams. So this scale is accurate, okay? Yes, accurate. It's an accurate scale, but it's not precise, okay? No precision. If I average out the numbers, I get the right answer, but I can't just trust one measurement. I have to keep doing lots of measurements and average them out to get a good answer. And that's because this balance has really low precision. It keeps bouncing around a lot, okay? So we want both, obviously, right? We want the scale to give us the accurate result, and we want to get the same result every time. We want it to be repeatable. Okay. At this point, that's all the notes I have for you. If you missed anything in this video, I have a copy of these notes available to you back in Schoology. Again, you go back to our front page, and it's right next to the textbook. There's a link to the notes back on the front there. Okay? You can go rewatch this video or get a copy from those notes if you missed anything. And I'm hitting the wrong button. Here we go. Here's the stop.